Welcome to the first technical session of the morning. My name is Diane Martin. I'm an associate professor of computer science in the Electrical Engineering and Computer Science Department in the School of Engineering and Applied Science at George Washington University. I want to welcome you on behalf of the president, the dean, and my department chair at George Washington University, since we are the university host for this conference. And it's a real pleasure for me to be able to introduce the speakers in this first technical session, particularly since I'll be introducing a cowgirl, a pioneer, and a trailblazer. Our first speaker is a cowgirl. Her name is Mary Jane Irwin. She has a degree in mathematics from Memphis State University and a master's and a PhD from Computer Science, University of Illinois, Urbana-Champaign. She is now a professor of computer science and engineering at Pennsylvania State University. She has very diverse research interests in computer architecture, VLSI, computer arithmetic, electronic CAD tools, lots of different research interests. She has a very impressive array of professional service. She's been on editorial boards of journals. She's an elected member of the Computing Research Association, and she was recently elected a fellow to the IEEE. And rather than take up any more time, because she really doesn't need any introduction, let me introduce Mary Jane Irwin.
Thank you, Diane. I left my cowboy boots at home. Before I get started, first I want to make a slight apology. I'm really not here. I'm in San Diego in the midst of a conference, a very important conference and a very large conference. I happen to be on the executive committee. So I snuck away yesterday, and I'm going to have to go back for a meeting tomorrow. So I'm going to miss most of the conference. And I find that really disappointing. So if you want to talk to me, you need to find me before about 2 o'clock, because that's when I'm going to end up back in real space rather than in virtual space. First slide. Okay, what I'd like to talk today about is design challenges in massively parallel fine-grained architectures. I would guess that everyone in computer science and engineering has heard about the high-performance computing and communication program. In fact, if you hadn't before this morning, you have after Anita's talk. I want to make a little aside here. Maybe I've become sensitive because of the realignment of my department, but I think we need to think about a vocabulary here. There are lots of sisters with a Y in computer engineering who think of themselves as computer engineers and not specifically computer scientists. So I've tried to make a very conscious effort to change my language to be computer science and engineering so that we embrace all of the sisters in the various areas of computer science and computer engineering. Back to the talk. The goal of the HPCC program is to accelerate the development and use of future generations of high-performance computers and networks. This is taken directly out of the HPCC document that was generated by the government. The program consists of 5 thrusts, and the work I'm going to be presenting today falls in the high-performance computing systems area of the HPCC program. Its aim is to develop scalable computing systems with associated software, systems which are capable of sustaining at least 1 trillion operations per second, that is teraops, in performance. Note the 2 highlighted words, scalable and teraop. Scalable is important so that designs of current generation machines scale automatically to future generation machines. And teraop, of course, is the real performance measure. Remember, teraop is 12 zeros. So we're talking about a significant number of operations here. Right? 1 followed by 12 zeros. We'll see these two words highlighted in several slides for the next half hour. Next slide. To illustrate the design challenges of massively parallel fine-grained architectures, I'm going to use, not surprisingly, a specific architecture project we've been working on at Penn State. Our machine is named the MGAP for Micrograined Array Processor, and it is an example of a massively parallel fine-grained architecture. Our goal in this project is to design, implement, and apply a massively parallel fine-grained coprocessor which provides at least a tera-op on a single board. And the particular characteristics of the MGAP are that it is scalable in performance, note that highlighted word, and I'm going to, at the very end of the talk about future generations designs and show how they scale automatically from the current generation that we're working on. Scalable in number of processors. Embeddable, that is, fits on a single board, and in fact, future generations we're hoping to fit on an MCM, or multi-chip module, which we also heard about this morning. Moderately easy to program. Versatile. Versatile, that is able to solve a fairly wide range of problems, but I'm not talking about a general purpose architecture here. I'm really talking about an application-specific architecture, and relatively low cost. The outline of my talk today is as follows. First, I'm going to describe the architecture of the MGAP system as an example of a massively parallel fine-grained architecture to set the stage. Then we'll look at techniques for speeding up low-level operations by careful mapping of operands to the architecture and by using a special kind of arithmetic to get digit parallel operations. I'll then briefly show how two very different applications can be mapped onto this style of architecture and give some specific speed-up figures for what happens when you do apply that mapping to an application-specific, massively parallel architecture as opposed to a general-purpose machine. Finally, I'll summarize the list of challenges that I'm going to mention during the talk in the design, implementation, and application of these sorts of architectures, and I'll give you a brief sketch of our plans for the future. This is the schematic of the board-level architecture of the MGAP, and the details aren't important for our discussion today, but what is important is that it fits on a single board. It's a coprocessor, in fact, a coprocessor in the Sun 4 system. And the heart of the board is this processor array that you see down at the left-hand side. It's an SIMD processor array, and that's where the massively parallel fine-grained computing core exists. The board also contains some staging or I/O memories and a reasonably fast onboard scalar processor and the VME interface for communicating with the host CPU. The next slide is a picture of the board. Doesn't show up too badly. You can see the array, it's only partially populated, of custom VLSI chips. That's the computing core, that's the processor array, the massively parallel fine-grained architecture. It consists of 32 custom CMOS VLSI processors. The rest of the board is the supporting memory, the staging memory, the scalar processor, and the VME interface. Next slide. What I'd like to do is focus in on the processor array, which is the component of interest for the talk I'm giving here today. And our aim in designing this processor array was to fit as many processors as possible in as small a space as possible and to make them go as fast as possible. So what we had to do was keep each processor simple, hence the name MGAP for micrograin and the name of my talk, fine grain processing. Each of these processors is extremely simple. It is a SIMD, that is single instruction multiple data array, of 2D mesh of fine grain processing elements. So it's nearest neighbor connected. We looked at other communication structures and decided that if we really wanted to fit as many processors as possible on this board, we had to have simple communication, so we settled for nearest neighbor. The board that we have that is up and running and has been since December, it runs at 25 megahertz. It has 16,000 of these processors in that array of 32 chips. Each of these fine-grained processors can execute 2 operations per clock cycle, And if you do the multiplication, you find that we almost met the goal of a teraop. It gives 0.8 teraops. Okay. This next slide is a photomicrograph of one of those 32 chips. It's fairly modest technology. It's 1.2 micron CMOS. That contains 512 of those fine-grained processors times 32 on the board gives us the 16,000 processors on the board. It fits in a 132 pin grid array. Now what I'd like to do is focus in even further and look at one of those simple processing elements and show you how fine-grained it is. First, it is very simple. If you think about a typical processor in a machine, this is pretty minimal. It consists of a dual-port local memory, which is really the register file, which in the current machine only has 16 bits. Okay. 2 functional multiplexers. These are 8x1 multiplexers, and we're going to look at those a little closer in the next slide. Configuration multiplexer, PE-enable, disable flip-flop, which masks the PE from participating in operations when it's set. Link flip-flop, which is used for communication to the ports on the north, east, west, south, or north, south, east, west. But if you set north, east, west, south, you can use an acronym NEWS, which has become popular in this sort of architecture. The next slide shows a picture of the layout of a pair of processors. It's not important, the detail isn't important here. What is important is if you want to get as many processors as possible in as small a space as possible, you end up drawing each transistor by hand. And each of these was done by hand. Of course, you do one processor and then you pair them together and array it. So we spent a lot of time on an individual processor trying to get it as compact as possible and paying attention to interconnect, of course. There are about 100 transistors per processing element, and so only about 50,000 transistors per chip. So it's not terribly aggressive if you start looking at industry processors which contain 1 million, 2 million, 10 million transistors per chip. Okay. Well, how does this do in operation? One thing you noticed is there's no adder, right? There's no adder in this processor. How do you do arithmetic? Well, you do arithmetic in the multiplexers. We have 2 functional multiplexers. They're 8x1 muxes. And for those of you who logic design is far in the distant past, let me sketch multiplexers very quickly. A multiplexer has, in fact, the ones we're using, 8x1, has 3 address lines, which selects one of 8 inputs to gate to the output. Okay, simple address. All the logic is done in the functional multiplexers. And now's the time for the overlay. Okay, so what if we wanted to do single bit addition, where we have the add-in, the aug-in, and the carry-in? Those are A, B, and C. And those are, we're going to assume they come out of the local memory and one out of the configuration multiplexer, which is an input to this cell. And we know the logic equations for adding 3 bits together produces a sum and a carry, and that's the truth table of sum and carry. F1 is the sum and F2 is the carry. So what we do is we introduce to the left function multiplexer the 8-bit information for sum, and to the right multiplexer the 8-bit information for carry. Those are the instructions that are broadcast to the array, and we find that we do have an adder that is capable of doing 1-bit addition. In fact, it's much more flexible than a single-bit adder. What we have is we have 256 for a 8-to-1 multiplexer, different logic operations. So it's much more flexible than the typical ALU. Okay. In most fine-grained SIMD processors, actually I want to go back to the previous slide, not the overlay, but just the picture of the architecture. Sorry. In most fine-grained SIMD processors, all PEs talk in a single cycle to other PEs in a similar direction. So you set it up so that all PEs talk north, or they all talk south or east or west. And our architecture is slightly different in that we have this configuration multiplexer which allows different PEs to talk in different directions in the same cycle. So one PE can be talking north while another is talking south, while another is talking east and another west. And this has interesting implications for operand assignment. What we have to do is set up the configuration multiplexer, and that determines which input port is coming into the input labeled C on this slide. In a fine-grained architecture, where we only have 16 bits of memory in each processor, a 16 or 32-bit operand is too large to store and process in a single PE, so we have to distribute it across several PEs. Store an operand digit in a number of PEs. One option is to store the operand in either a vertical or horizontal linear array. But a better choice is to use the snake configuration, which is on the next slide. Because if we're looking at higher level operations, what we're worried about is shifting a word of information from one location to another. And if we have it in a vertical direction, store operand in a vertical configuration of PEs, moving things east and west takes one cycle. But moving things north and south take the number of cycles determined by the precision of the operand. If we store it in a snake configuration, what it's going to do is it's going to take square root of the precision times square root of the number of PEs to shift both east-west and north-south. So if we look at higher level applications, this is a better choice for storage. And you can see why it's called snake configuration. What we want to do is we want to assign each digit of the operand to a processor where we keep it next to its neighbors in the operand numbering, and that does this. So we have what we call a snake word processor, which is composed of a number of processing elements, and the only reason that we can do this and that other similar fine-grained architectures can't is that we have this programmable interconnect, so we have the capability of talking different directions in one cycle. Okay. Now I'd like to move beyond the architectural issues now that we have a sketch, and look at some low-level and high-level algorithmic issues. First, I'm going to illustrate how to do digit parallel arithmetic on a fine-grained architecture. I'm going to use the MGAP as the example. Then we'll look at two applications, one of which uses what I call digit pipelining. And these are two very desirable performance enhancements in an architecture like the one we're talking about this morning. So here we have our snake configuration. I'm going to assume that the most significant digit is stored in the upper left-hand corner, and the least significant digit ends up in the lower left-hand corner, and that we have this snake arrangement. So this will give us 16 digits of precision, and I'm going to talk about digits rather than bits just to keep things simple. And I've divided each of the boxes into 4 quadrants so I can write down the two numbers that we're adding together and show the sum and carry result of the addition. Okay. So here's the movie. What we're going to do is we're going to look at adding decimal numbers to keep things simple, right? 2 decimal values, and you note that the interesting thing about the numbers that I chose is this is a computation which will cause the carry to ripple from the least significant end to the most significant end. So what I've done is I've shown the aug-in stored in, I guess, the right cell, upper cell, and the add-in stored in the left upper cell. So there's the initial state. Okay. So the first thing we do is we add the 2 least significant digits, 9 and 1, and we get 10, right? The next thing we do is we pass that carry to the next most significant position, and then, we add, we add that carry into the next most significant position, so 9 plus 0 plus 1 is 10, right? Then we pass the carry to the next most significant position. I'm not going to go through all of these. I think the next slide. Voila! So after we do this 16 times, we have the sum stored correctly, right? We do a digit add, pass the carry, a digit add, pass the carry. We have to do this as many times as we have digits in the operand. Pretty slow. Okay. How can we speed this up? Well, we start back with the original picture, back with the add-in and the aug-in stored up there. And what I'm going to describe to you is an operation that's called using signed digit numbers and signed digit arithmetic. I'm going to use very different rules here. What I'm going to do is I'm going to say, well, I'm going to form an interim sum, which I abbreviate here IS, and an interim carry in all PEs in parallel, such that the interim sum is strictly greater than -9 and strictly less than 9, so in the range -8 to +8. And the interim carry is strictly greater than -2 and strictly less than +2, so it's in the range -1 to +1. So I've done that in parallel in all of these processing elements. For example, in the least significant cell, I add 1 and 9, which gives me 10. Those are both perfectly legal choices. The interim sum is 0, and the interim carry is 1. Fits in the range, no problem. Now, I have a problem with the other ones, right? 0 plus 9 is 0, 9, right? But the interim sum cannot be 9. It has to be in the range -8 to +8. Well, I know 0, 9 is equivalent to an interim carry of 1 and an interim sum of -1. Remember, the carry is shifted, so it's really 10. So 1 followed by a -1 is 10 minus 1, which is 9. So we have an equivalency here. And note that those are in the legal range. An interim sum of -1 is fine, an interim carry of 1 is fine. So everything in the bottom half of the squares is perfectly legal. Okay, next slide. Then what I do is I pass the interim carry in every processing element to the next most significant PE in all the PEs in parallel. So I've just pulled that 1, that interim carry of 1, and passed it to the neighbor. Okay? And then I finish off with adding that passed interim carry to the interim sum that's sitting in the cell in parallel. And note that because of my restriction on the interim sum and interim carry, the interim sum is in the range -8 to +8. The interim carry is in the range -1 to +1. My sum is going to be in the range -9 to +9, or strictly less than 10 here. And there will be no further carries, and I'm done. Right? So in one cycle, well, three cycles, but not 16, I form the interim sum and interim carry. I pass the interim carry. I form the final sum, and I'm done. And it doesn't matter how many digits I have in the operand. All of the digits are working in parallel. In fact, what I've done is I've restricted the carry to 1-digit position. Okay. Okay, we use this sort of digit parallel arithmetic approach in all of our low-level algorithms, and we've been working on optimizing those low-level algorithms, trying to minimize the number of cycles and the amount of storage, etc. In particular, we've looked at the primitives that we need for the higher-level operations that we've been working on, and here's a typical instruction count for some of these low-level operations. This is assuming base 4 arithmetic rather than the base 10 example that I gave you. And it's assuming snake configuration, and in fact, it's general for any precision, so that's shouldn't be 16-digit precision down there. What n is in this picture is how many digits precision there are. So you can see that digit shift, where I'm just shifting a digit from one position to the next position, is a constant time operation. Word shift is square root of n because of my snake configuration. It doesn't matter which direction, it's still square root of n because that's the boundary. Comparison is square root of n because at the end of the comparison operation, I want to store the result of that comparison in all the processing elements that compose that word, and to do that, communication is a square root of n operation. Addition and subtraction are constant time operations independent of the precision of the operand, and multiplication is a linear operation, not an order n squared operation, which is what we're typically used to, but a linear operation. Okay, this gives number of instructions, but let's step back a little bit and see what's going on here. It looks like 25 cycles for an addition. Well, that's pretty expensive. But stop and think that if I've got 16 digits of precision and I've got 16,000 processors and I keep them all busy, that means I have 64 times 64, if I do it in a square array, 64 times 64 operands. So I have 4,000, or 4,096, 4K operands. So I'm doing 4K additions in 25 cycles if I'm running the entire array. So what that means is it takes me about 1,000 nanoseconds running at 25 megahertz to do 4K adds. So what I'm getting is about 4 billion additions per second. I get that because of the parallel arithmetic and because of the massively parallel nature of this processor. And it gives us about 50 million multiplications per second. Okay, so certainly massively parallel. Okay, being able to easily exploit such digit-level parallelism means that I either have to program at the assembly language level, and we found out really quickly that we didn't want to do that, Or we want to use a language in which the user can specify operand digits. Very different than our normal concept of thinking about operands. I've got to be able to get down to the digits of the operands. And then we have to have a compiler which can detect such digit-level parallelism and exploit it, produce parallel code. And we looked a long time and we thought about coming up with our own language for this machine, and we decided that was certainly the wrong move, and we looked more closely at object-oriented programming languages, and C++ turns out to be the perfect choice because in an object-oriented language we can define the objects. So we start defining the object at the digit level, and then we build words from digits, and then we build arrays, or we call them shapes, stealing from star C, shapes from words. So we have a handle on getting down to the operands at the digit level. And we've been working on such a parallelizing compiler for the MGAP for C++ code. And the compiler's actually been working successfully for a couple months, although every time we try a new application on it, we find we have to add more to the compiler. So it's certainly in development. Okay, next slide. What I want to do now is shift to looking at applications. And this processor is certainly good for a number of applications, but it's still, remember, not general purpose. It's special purpose. It turns out it's good for lots of things in image and signal processing, for edge detection and various kinds of transforms, for doing connected component. In image processing, FFT's filtering, we're looking at some data compression. Lots of things in general numeric processing like matrix addition and multiplication. We're looking at SVD and a number of other things. And what I want to show you this morning very quickly is an example of a problem that fits in computational fluid dynamics that we got from the CFD folks at Penn State, and a problem in searching that we're working with the computational biologists in our department. Okay. This is an example of a lattice gas dynamic problem that we got from the CFD people. What you have in a lattice gas dynamic problem is that you've got particles, right? And you've got cells. And you have a formula that says, if I'm a cell, and I look at incoming particles coming in from these two, this single or these two or these three directions, I know in the next cycle I want to send particles out in another particular direction. And the CFD folks have all of these mappings worked out. And so what we have done is map this into a cellular automata model which maps perfectly, easily to the MGAP, where each PE is a particle. Right? And what we have is we have 32 different collision models, which is what the CFD folks gave us. So we model every single particle coming in, every pair of particles, every triple, some subset of 4, 5, and 6 particles. Okay. What we have to do after initializing the array is we have to just go through this loop infinitely many times, right, till the system reaches a steady state. We input articles in this cellular automata model. The only tricky part is we have to map our news architecture, our nearest neighbor connected architecture, to a hex mesh architecture, which is what this model requires. Then we match the collision patterns to decide which way the particles should go out. Then we output the particles. Then we go back and input, process, output. So we just do this until we reach steady state, which is after millions of operations. Well, we have running code on both our first generation MGAP and on a Spark 2, and in fact the Spark 2 code was optimized by the CFD folk, and they've been working on this for quite a while. They get about 90 iterations a second on their code, which has been optimized for the Spark architecture, and we get on the MGAP running code written in C++ and compiled by our compiler, 20,000 iterations per second. So we certainly get the kind of speed ups we would hope to see. 2 minutes. Okay, the next slide shows a picture of one of these, it's kind of hard to see, one of these lattice gas problems where what we've done is we've got only 8K processors working. We're injecting particles on the left and removing particles on the right, and we have this boundary in the middle, and it's been running for 10 million iterations. And you can see the back side of this obstruction there are fewer particles. So we're starting to see eddies form and develop. The next problem I want to look at quickly is a problem faced by molecular biologists when comparing an unknown biosequence with a set of known sequences to find the sequence with maximum match, something that fits in the Genome Project. So what we have is we have two character strings that we want to compare and compute the best match. So if what we're doing is computing the score, the C's match, so alpha has some value for when we have a character match. Delta AG says A and G don't match, and there's some penalty associated with that not matching. T and blank don't match. Once again, we have a penalty. G and G match, so we have alpha, A and A match, and blank and C don't match, so we have some penalty. And what we want to do is we want to compute the best match, find the best match. And this actually simplifies what we're really doing, this picture, because what we really got is we've got a given sequence of length m, which is the unknown, and we've got a huge database of sequences of length n, where n is typically much larger than m, and we want to find the best match. So what we're doing really is doing a sliding pattern match. Okay, the next slide, which I'm not going to really have time to go into, shows how we map this onto the MGAP, and it's a dynamic programming problem. So what we do is we start, we load the unknown into the array, and we start the known sequences. So you see we have B pattern, 1, 2, 3, 4, and they're skewed, so that we have a back diagonal flow of computation going through the processing array. So once the first cell, the uppermost left cell, has stopped processing on the first sequence, we start the next sequence. So what we've really got is we've got strings of back diagonals flowing through this array. We grab the result out of the bottom right-hand corner, and we look for the best match. So what we're doing is sliding string comparison. The next slide shows, these are simulated. We don't have this problem running on the MGAP yet, but a simulated, we have it running on our simulator. We have 104-letter alphabet sequence comparisons of length 100 characters, which our literature search shows us can be done on the Cray2 in about 6.5 seconds, on the CM2 in about 4.7 seconds, and on the MGAP in 0.001 seconds. Okay. I hope in this talk I've illustrated several of the challenges facing the designers of massively parallel fine-grained systems in the areas of architecture, trying to keep as many processors as possible on the board, in algorithms, making sure we're using them efficiently, both at the digit level and at the operand level, and the problems that we're facing now in compiler development, in particular being able to detect and exploit that parallelism at the fine-grained level. Okay. So what's next for us? Well, we have the MGAP1 up and running and the compiler for it up and limping. And we've started designing the MGAP2, and we, in fact, have a processor pair ready to send out for fab at the end of this month. We know we can fit 4 times as many processors in the same number of chips. Part of that is because we've sized down the processor. That is, we've spent more time working on the layout so we can fit it in smaller space. It's actually going to have 32 bits of memory rather than only 16 in each PE. And we're going to use 0.8 micron CMOS rather than 1.2. We're going to double the clock, the system clock, and once again multiplying the numbers, that gives us optimal, our 6.4 teraop maximum performance. And the next generation we're looking at putting on a multi-chip module, and are hoping we can once again quadruple the number of processors and once again double the speed and get something over 50 teraops. Thanks. Okay. We do have a few minutes for questions if somebody has one. Okay, I'll repeat it if. There's one back there. Remember that this is a coprocessor. It fits in a Sun 4 system, and it works across the VME interface. And so at this point, we're, of course, using the operating system that's sitting on the host. And we're, of course, running the compiler on the host and then download the code into the coprocessor. So we haven't faced any operating systems questions, and we're not, other than I/O, which is a big problem to this board, we haven't encountered any problems. But once you build a prototype like this, you start to discover what problems are lurking there. That's why I think it's nice to think about a generation, several generations of machines, so you have a chance to do right in the next generation what you did wrong in the current generation. There's one here. And then I'm sorry, I said I was going to repeat the question.
Hi, I'm Melody Mo with San Jose State University. It's a very interesting talk. I have several questions.
Okay.
First, have anybody in your group consider fault tolerance in your architecture, or what do you anticipate the error rate? Secondly, anybody think about using your design for neural network computing? Third is, what are the most recent reference to your work? Okay, thanks.
Okay. The first question was on fault tolerance. The only fault tolerance we have is that enable-disable cell where we can mask out a row of processors. Of course, if we lose the links, we lose the entire chip. We have route around on the board. You can only do so much at one time, and we are thinking about fault tolerance, particularly for the MCM. The next question was on neural nets. We have not in particular looked at neural nets, but I think it is a natural architecture, and there are groups in the department that are looking that direction. And the third question was about reference. I can give those to you offline. We've got a number of application references. I'm working on a paper that I'm going to submit to computer, which of course is potential reference. There have been papers at ASAP, which is Application-Specific Array Processors, at ICASP, which is the Signal Processing Conference. Those are probably the best two references. And there was a question back here, and then I think I'll cut it off. The staging memories we haven't overflowed yet. They're not huge. They're less than a megabyte sitting on the board. I think we just haven't pushed the board hard enough yet. We know that 16 bits of memory in each PE is not enough. We're hoping for the general range of problems we want to solve. It's fine for these cellular automata type problems, but if you want to start to do problems that have multiplication and division, you run out of local storage very quickly. 32 bits we think will give us enough. Remember, what we're doing is spreading the operands so that each PE only has to dedicate 3 bits to an operand digit. So 16 bits still gives us 5 registers. Still not enough. Getting the stuff, yeah, well, you want to use this. It's not a general purpose machine. Once again, you load it up, you compute 10 million iterations or 20 million iterations, and then you flush it out. We're starting to look at other problems where flushing it out is a problem. We really want to look at what's in the array more often than every 10 million iterations. And we're not going to solve that in the next generation, but it's things we're scratching our head in the MCM design, trying to see first if we can move the staging memory closer to the PE, and second if we can get output from the PEs more easily without impacting this being able to communicate in one cycle. Challenge. Thanks.